Hi. So, welcome. Yeah. So we're gonna explore Sylow's theorem. Sylow's theorem. This is a 21st exploration. 21st exploration of Sylow's theorem. And so far we've been just Sylow's theorem says, look, suppose we have a group G whose order is p to the alpha times m. Okay, where p and m are relatively prime. Does that necessarily mean that uh, there exists some subgroup h of g such that order of h equals to p to the alpha, right? That's the question. We don't know if this is true or not. And so far we've proved a couple of special cases. In particular, we resolved that if g is cyclic, then apparently the statement follows. But then we had the case of what if g is not cyclic? What are we going to do then? And in the previous video, we're exploring an idea. Let's just either see if it works or dispose of it completely. And the idea was, okay, it's hard to prove, it seems hard to prove the entire thing, so why not why not just prove a special case? Suppose that instead we had that the order of g was p squared times m, where p and m are relatively prime. Well, now we're exploring this idea of showing that actually, suppose we said instead that there exists some subgroup L of g such that or such that z mod pz cross z mod pz, right, is isomorphic to L, which is a subgroup of G, as we said before. So suppose we found that some subgroup of G was isomorphic to Z mod PZ cross Z mod PZ. Wouldn't we then have proved that the order, there exists a subgroup of G, namely L, and what's the order of L? Isn't the order of L equals to the order of Z mod PZ cross Z mod PZ, given that Z mod PZ and L are isomorphic? So what would be the order of L? Wouldn't it just be P squared then? They're not things. What are they? Okay, if the order of L is p squared, alright, so, right, so this seems like an approach, but again, how do we know that there is some subgroup of G which is isomorphic to Z mod PZ equals Z mod PZ? Right, in particular, I mean, can we produce an isomorphism? Or if we can't produce an isomorphism, is there another way to show that two groups are isomorphic? Well, yeah, we're not sure about this. It seems pretty difficult to show that. It seems pretty difficult to show that Z mod PZ cross Z mod PZ is isomorphic to some subgroup of G, given that we don't know what the subgroups of G are, and G could be arbitrary. Yeah, this approach doesn't seem to be helping us much. So what else can we try? What other approach might help us? Well, let's see. What about if we've been all this time trying to find a subgroup of order G, etc.? What if we constructed one? Right, so what if we found some subgroup H of G such that let's say some subgroup, let's give it a different name, K. So we found some subgroup K of G such that order of K, let's say, equals to P to the I, where I well, if I is alpha, we're done. So let's suppose that I is actually less than alpha. Okay. Now, is there any way to extend the subgroup K? That is, we get this. So we have the group G. Okay. Order P to the alpha times M. We get the subgroup K. We get some subgroup K, let's say, of order P to the I of some order, and then we extend it. Right. So here's the key idea: is we extend K so that it includes, we add, we extend K by some set, let's say S, so that what we end up having is, here of course we're saying order of K equals to P to the I, and let's say that we get some P to the alpha minus I elements and add them to the set S. So the order of S, is being, okay, let's erase this. Well, the order of S is being taken to be equal to P to the alpha minus I. Okay. So suppose we could get some subgroup K and extend it to a larger group, right? So perhaps maybe it's difficult for us to perhaps find a subgroup of order P to the alpha, but the question is, can we create one? Right? Can we create a subgroup of a given order? Right? So, I mean, we don't want to be bogged down by the specifics of this problem, so let's try and think in general for now. Let's think about how to extend, perhaps the study of extensions. Uh, we're going to call this extensions of a group. Perhaps a study of extensions of a group will give us some new insight into Sylow's theorem. How to extend a set to a group. Let's say that. Right? So how can we extend a set to a group? Right? So suppose we have some set of elements, like let's say, it's perhaps better to even work with a concrete example just to see what we're doing. What's the easiest set to work with? Well, why don't we work with our good old Z mod somethings? Okay. Think about Z mod, what? HZ? Sure. Z mod HZ. What elements does it have? 0. Can we say it has 1, 2, 3, 4, 5, 6, 7? Okay. Suppose we got some set. Let's say some subset of Z mod HZ. Let's call it S. Let S be 1, 3. No, let's not let it even not have the identity in it. What the heck? Let's have some fun. Okay, hard eraser. Let's say instead we get, let's say 2, 5. Okay. Now, is the set 2, 5 a group? Well, does it even have the identity element? Okay. So, if we were to extend S to form a group, what would we need to do? Right? How to extend S? Should we come up with a symbol for an extension? Sure. What's a good symbol for extending something? When we extend, we are pushing something. Okay. So let's say this. S arrow, that's S extended. Right? So the extension of S, right? Well, suppose we get 2 and we throw in the inverse of 2, right? What's the inverse of 2 in this case? Okay, let's just write as 2 inverse for now. And suppose we get 5 and we throw in the inverse of 5. Oh, sorry. Well, we're extending the group, we're extending the set, so isn't 5 already an element? Okay, how about 5 inverse? Well, okay, we have 5 inverse, sure, because at least if we're going to form a group, doesn't it mean that every element must have an inverse? Okay, so 2 has an inverse, 2 inverse, 5 has an inverse, 5 inverse. Okay, what about, well, are we done? Right. Mustn't a group also have the identity in it? Well, what's the identity in this case? Isn't it just 0? Okay. So are we done then? If we throw in the inverses and we throw in the identity, are we done? So, for instance, well, what's 2 inverse exactly? Isn't 2 inverse the same as, uh, what do you add to 2 to get 0 mod 8? Right. Could we say 6? Okay. 6. What about 5? So do we even need to write them out like this? Sure, sure, let's write them out like that. What about 5? Okay. What's 5 inverse? What do we add to 5 to get 0? Is that 3? Okay. 5 plus 3 is 8. Is 8 0 mod 8? Alright. And let's leave 0 there. So question, is this a group? Is 26530 a subgroup? We could say a subgroup of Z mod 8Z. Right. So let's see, is S extended a subgroup of Z mod 8Z is the question. Right. Is it? So let's think about that. Well, do we have inverses? Right. What's the inverse of 2? Was that 6? What's the inverse of 5? Was that 3? What's the inverse of 0? Is that 0? Okay. So can we say that everything has an inverse? Alright. Is it closed? Is the question though. Right? Can we guarantee closure? What's... Well, okay, if we add everything to its inverse, we're fine. But let's add things that don't necessarily inverse. What's 6 times 5? Sorry, 6 plus 5. Right. 6 plus 5 is what? 11. Okay. What's 11 mod 8? Right, so let's just write everything mod 8. What's 6 plus 5? What's 6 plus 5 congruent to mod 8? Is 11 mod 8 3? Okay, just write like this, 3. Well, is 3 in the group? Sure. What about 6 plus 3? Is that 9? But what's 9 mod 8? Is that 1? Okay. Is 1 in the group? Or in the set S extended? No. Okay. So if 1 is not an element of S extended, how can S extended be a group, right? If it's not closed, how can it be a group? Well, so how can we fix this? How can we adjust S extended so that it actually becomes a group? Right? So maybe we can add in closure as well. So that is S extended, we could set it equal to, well, let's see, 26530, and then from here, let's add in all the this actually becomes a challenge, doesn't it? Because okay, so right, so we get 26530 and we want to add in everything to make sure that it's closed, right? So there's this fear that, for instance, we saw that 6 plus 3 gives us 1, but one is not in S extended. So S extended can't be a group. But what if we throw in 1? Would we have a group then? Well, doesn't that depend on what 1 plus 3 is? But now 1 plus 3, what's 1 plus 3 going to give us? 4. So, but is 4 in S extended? No. So are we going to throw in 4 as well? But if we throw in 4, well, what's 4 plus 3? That's 7. Is 7 in our group? No. Okay. So we're going to throw in 7 as well. Alright, what about 7? Well, but don't we have, what is this? 1, 2, 3, 4, 5, 6, 7. But isn't 1, 2, 3, 4, 5, 6, 7? Uh, is it, isn't that just the same as z mod 8z? So we've just extended the set 2, 5 to a group, sure, but the group turned out to be the group we started with, z mod 8z. So why is that interesting? How is that interesting? So perhaps not. Or maybe the question now to ask is, sure, well, how did we try to extend it? We started from 2 and 2 inverse, 5 and 5 inverse, and then 0, and we saw that it wasn't closed, and we added the element 1. Well, maybe if we had added something else, wouldn't it work? That is, suppose we hadn't started with, what if at this point here, we'd started with a different element? Um, Actually, does it matter even which element we start with? So the question was, well, what if, so here, how did we end up adding 1 to the to S extension? Well, the way we added 1 to S extension was by coming here and checking 2, 6, 5, 3, and 0. Okay. Well, we found that we did the addition, right? In this case, we did 6 plus 5. No, I think we've done 5 plus, no, what did we do? Or 6 plus 3. We got 6 plus 3 and that gave us 9. What's 9 mod 8? Well, we said that was congruent to just 1. And because 1 wasn't in our set S extension, we had to add 1 manually into our set S extension. But maybe the question is, well, why did we have to, well, if we didn't, the question is, if we didn't add 1, would S extension ever be a group, right? So, and the answer is, how can it be, right? If the sum of two elements is not in the group, how can that thing be a group, right? So, did we even have a choice? Didn't we forcefully have to have 1? Didn't we forcefully have to have 4? Didn't we forcefully have to have 7? So, okay, so here's the claim we're trying to make right now. So again, let's study how to extend a group to another group and see maybe studying these extensions of groups will enable us to figure out if there is some subgroup, if actually there's a subgroup of order p to the alpha. So this might turn out to be a long exploration, but that's perfectly fine, so long as we're learning stuff along the way. But now we're making this following bizarre claim that if we got S extension, if we set S extension equal to, if we started with S equals to, what are we calling it? 2, 5. Okay. Is it necessarily the case that the only smallest group, S extension, had to be equal to G, the group itself, in this case Z mod PZ, Z mod HZ? Right. Does that make sense as a question? That is, could we have extended S equals to 2, 5 to some other group, but had it be the case that the group that we extended 2, 5 to is different from Z mod HZ? Right? Is the extension of S unique? Let's put it this way. Is the smallest extension of S is the smallest order extension of S equal to G? Right. Let's see if this makes sense as a question. Right, anyways, we'll proceed from here. We actually did run out of time. So right now it appears that, look, all the obvious approaches to proving Sylow's theorem haven't really been working for us here, which means that perhaps we need to manually create a subgroup of order p to the alpha. And to manually create a subgroup, one approach we could use is to figure out how to extend a set. How can we extend a subset S of a group if we have some subset? If we have, so here's really the approach we're trying now is, and we're going to study this for a while and then see if it gives us some insights into Sylow's theorem. If S is a subset of a group G, how can we extend S to give us S extension, some subgroup of G? Right, we're trying to study how to extend a subset into a group, basically, right? So that's what we're dealing with now. And we'll probably come up with theorems and prove those theorems in this exploration of it. All right. So thank you very much for watching this video, and have a relentless week. Bye.